Well, hello there, everyone. It's the top of the hour. I'm going to go ahead and get started. Looks like a couple people are still connecting their audio, but I think we'll get where we need to be. So I want to welcome you to this month's installation of NCAT's From Research to Implementation webinar series. This week, our topic is practical forensics for asphalt pavements. Really exciting topic, something that I definitely could have used when I was with the DOT years ago, and I was being asked to come out and look and, hey, what happened to this pavement? Why did it fail? So hopefully this is some information that you guys will each get to be able to use there. So this week with us, we've got Buzz as always, and then we've got Jason Nelson from the track. So I'm going to give you guys their intros real quick, and we'll kind of go from there. So Buzz worked for 12 years for the Alabama DOT and 2 years in the private sector before becoming NCAT's first test track manager in 1999. He served as NCAT Associate Director and an Auburn University research professor. Buzz is now the technical director for the Asphalt Pavement Alliance. So we're so lucky that he is still able to work with us and helps us with a lot of things. So Jason Nelson is the test track manager at the NCAT test track. He holds 2 bachelor's degrees and a master's degree from Auburn University. His master's degree is in civil engineering. He's been with NCAT for 20 years. His areas of focus are surface performance, fleet management, and road construction. He also enjoys refereeing football and keeping bees. So let you guys a little behind the curtain there with him for a moment. As always, please, if you've got some questions, just go ahead and put those in the comment box, and we'll address those at the end, and then we'll go from there. So Buzz, take it away.
Well, thanks, Travis. I'm gonna kill my video because I'm having some bandwidth issues right now. So y'all just bear with me on that. And if my sound gets bad, if you can jump in and let me know, I'd appreciate it.
Will do.
All right, thank you, sir. I'm killing my video, and always proud to be here with my good friend Travis, and today is a special day because Jason Nelson and I have worked together for a long time at the NCAT pavement test track, and I'm happy to be here with him today and talk about something. I've been making presentations on this for, I don't know, maybe 5 or 6 years. And it's based on the body of experience that we have here at NCAT and at the NCAT pavement test track. So I'm really excited to share some of the things that we've learned with y'all today with a very practical spin. So this is intended to be useful for practitioners in a very practical way. Hopefully you will agree with that. So as always, I start out with background, and then we get into some research and deployment, and then I come back with some takeaways. We're mixing it up a little bit this time because Jason and I have been in the trenches, pun intended, together at the track for a very long time. So we're going to kind of tag team a combination of research and deployment there in the middle. But the content is very much focused on what we have learned for the last 24 plus years at the NCAT pavement test track. Yep, the regulars here will know that the track essentially is a nonprofit research business, and so it kind of zeroes out every third year. And within these 3-year research cycles, the first part of the cycle is dominated by construction, which will happen this summer for the 2024 track, and then we have 2 years of fleet operations, and then the end of the 3-year cycles is dominated by forensics, where we go out and do cores and trenches and all kinds of non-destructive and destructive testing to figure out, okay, how do we interpret what we're seeing on the surface of the pavement? And so that really is the focus of the content of what we're going to share with y'all today. When I first got into speaking about forensics, I did a back to basics webinar for Napa, and so I was specifically asked to talk, within the scope of the 5th edition of the LTPP distress manual, the long-term pavement performance program distress manual. And so the kind of the classification of distresses, I'm going to use that type of terminology and that type of verbiage for my content in the webinar today. And I'm really actively trying and you can, by the way, you can download this document at that URL that I'm listing on the top of that slide that ends in 4421. But as I talk about all kinds of different topics, I'm really promoting Hey Napa. So if we have any participants in the webinar today that are not familiar with this, it's heynapa.com, heynapa.com. You can set up a free account. It doesn't cost you anything to do this. And what Napa has done in partnership with XBE is created an artificial intelligence system that's built on top of over 1,000 technical references, research reports, and reference manual specifications, procedures, those types of things. And you can ask it, very, very practical questions, and it gives you very practical answers. And so just kind of as a demo to kick things off this morning, I asked the question, how do I identify pavement distresses? And it just as a word of caution here, when I did this, the very last time I asked Hey Napa this question, it popped up a link to the LTPP distress manual, but it was the 4th edition. So Hey Napa is a great reference, and it's a great way to have free access to some documents that you would otherwise, PDF documents that you would otherwise have to buy. But for the LTPP distress manual, I'll encourage everybody to go to that dot.gov reference that I'm showing on this slide. Make sure you get the most current reference of your document. And that's kind of the one caveat that I have at this point with Hey Napa. They're continuously improving it. And so my hope is that little things like that will be worked out. But heynapa.com is a great reference for just any kind of issue related to materials, design, construction, or preservation. You get some really, really good unbiased responses from that. So if you look in that distress manual, it talks about, okay, what is cracking? How do we define it? What is surface deformation? How do we characterize that? Patching and potholes, surface defects, and then miscellaneous distresses. So it kind of groups the asphalt part of the LTPP manual into these 5 different categories. That manual, by the way, includes both asphalt pavement and concrete pavement. And of course, we're the National Center for Asphalt Technology. So the content of the webinar today is limited just to what the things that you see in asphalt pavements. In the world that Jason and I live in or have lived in for all these years, and this includes the work that Adriana Vargas has done off the track in pavement preservation. We like to, we use the LTPP distress manual because it helps us to understand what we're seeing and quantify what we're seeing. But we tend to focus in reporting on the MAP 21 criteria, which these are the federal reporting criteria for state DOTs for their networks. And it really simplifies condition to percent of the lane area cracked, the rutting that you measure, and then the smoothness that you measure, the International Roughness Index, or suspension travel in inches per mile for the Gold Car computer model. So we use both sets of criteria, and we're going to focus today a lot really on the LTPP manual. By the way, the LTPP manual includes a breakdown of different severity levels, but the MAP 21 criteria, for example, for percent cracking, it doesn't get into severity level at all. It's just based on the kind of the square foot area of the pavement, or the percentage of the pavement that's impacted by cracking. And so you have to make a lot of assumptions when you put those numbers together. So this is what bottom up fatigue cracking looks like. This is actually the thinnest pavement that has been built on the track. It was part of a 2003 structural experiment. We had 2 sections that were only 5 inches thick, 1 full depth neat asphalt, 1 full depth polymer modified asphalt. And the highest, when you have thin, the bending at the bottom of the pavement in response to passing loads, the higher strain magnitudes are in the longitudinal orientation, the direction of traffic. And that means that bottom up fatigue cracking, it starts in the transverse direction at the bottom of the pavement. And that's virtually a universal truth when you have kind of classic bottom up fatigue cracking. And in the case of this experiment, we cut cores. If you look real close to verify this, but you can see an arrow in the direction of traffic in the wheel path. And as I said, this is a bottom up fatigue crack, and is working its way up to the surface of that pavement. Now, this is true for relatively thin pavements because they start in the transverse direction and then they migrate up over a relatively short distance up to the surface of the pavement. But if you look at this core, they don't come straight up. They kind of meander as they work their way through the pavement structures. So just kind of keep that in mind. That becomes very important because I want to talk about two different scenarios for bottom up fatigue cracking working their way to the surface of the pavement. If you have a thicker pavement, like maybe a typical state route or interstate type of a pavement, even though those bottom up fatigue cracks start in the transverse direction, you're probably not going to see them manifest on the surface in that orientation. So what happens is the cracks tend to, even though they start in the transverse direction, they have enough thickness to sort of rotate up, and they interconnect as they've rotated up. So they'll start as a longitudinal crack, more or less continuous. It'll be kind of stop and start at, but then they interconnect. And this is for relatively thick pavements because there's enough thickness for this to happen. Now, once they interconnect, then you'll see cracking extend out away from the center of the wheel path, and then they interconnect to become alligator cracking. But it's important to understand if you have a pavement, and this is kind of a generalization, but if you don't know anything about that pavement, but you see a longitudinal crack kind of skipping around in near the middle of the wheel path, then that is an indication that that's a relatively thick pavement, something more than probably 5 inches thick. And that is bottom up fatigue cracking that started in the transverse orientation. A completely different thing happens on thinner pavements. On thinner pavements, there's not enough thickness for the crack to kind of rotate up and interconnect. So on thinner pavements, you see the classic transverse cracking. This is how it starts on the bottom, and so there's not enough thickness for that to change as it works its way up to the surface. Then it'll interconnect eventually into alligator cracking. So you see the same kind of alligator cracking in the end, but how they grow and how they interconnect is an indication of the thickness of the pavement that you have out there, which is kind of an interesting concept. Now, here's a case where, and this was a test section on the track that we were not expecting to fail as early as it did in bottom up fatigue cracking. And in fact, and I think Jason's got some slides he's going to show later in the webinar today that describe exactly what happened here. But this is a case where the pavement debonded between layers. So you have a relatively thick pavement that is then responding and behaving like a thin pavement because it debonded. So when it debonded, the top part of the pavement that was not then bonded to the lower part, it was less than 5 inches thick. So it did fail in bottom up fatigue cracking. But in this case, it really was kind of a middle up fatigue cracking, and it just only happened because it debonded the way that it did. And as I said, Jason's gonna give you some background on that, I think, later on in the webinar. So what you see in these thinner pavements, relatively thinner pavements, you see a lot of these transverse cracks. So these are some crack maps from a past research cycle. And there's some areas that are shown there, and there's always some exceptions, but you do see the classic transverse cracks that just have worked their way up to the surface. And I'm going to compare that to some other thicker pavements, and you see some transverse cracks that really are kind of some sort of thermal stiffness related types of cracking. But in these thicker pavements now, these are perpetual pavements, and so the cracking that you see is not in the interior of the wheel path. Generally speaking, the cracking is along the edges of the wheel path. And so when you see longitudinal cracking along the edges of the wheel path, and the wheel path you can see, even if there's not any rutting because of the wear pattern on the pavement, that's an indication to you that might be a perpetual pavement. That might be a really thick pavement or a relatively thick pavement. So to kind of back up and give you a summary of all that, when you see longitudinal cracking, cracking in the direction of traffic, and it's in the interior of the wheel path, near the middle of the wheel path, then that's an indication of bottom up fatigue cracking, or possibly middle up if you've had some debonding in there. But when you see longitudinal cracking along the outside edges of the wheel paths, that's an indication that might be a perpetual pavement, and that might be kind of pure top down cracking or near surface cracking. When you see transverse cracking in the middle of the wheel path, that means that's bottom up fatigue cracking in a relatively thin pavement, and that can also happen when the pavement layers debond. So this is a picture of some transverse cracking and some longitudinal cracking in Minnesota on US 169. These are the high traffic preservation test sections in the cold climate, half of the research partnership with a Minnesota Road Research Project with Minroad. And this is a different kind of case. The transverse crack that you see here is a classic thermal crack because of the extreme cold temperatures that they have there. The expansion and contraction and the movement of the pavement leads to these thermal cracks. They go typically from shoulder to shoulder, and in some cases they'll even go out into the outside of the paved area of the shoulder because there's such aggressive thermal cracking. And of course, this pavement, then in this experiment, we did crack routing and filling, crack sealing of that transverse crack, and then we did mastic patching of the longitudinal crack that you see there. And you might, if you're not from Minnesota, you might, or some of the other northern states, you might look at that and say, why is that longitudinal crack along the on the inside edge of the edge line stripe? So based on what I said previously, you might look at that and say, well, is that a perpetual pavement, and is that a top down crack? What you need to know about this pavement, again, and that it's important in forensics, learn everything you can about the pavement structure. There's a lot of farming in this area, so the shoulder, and you kind of get a view of it in this picture. The shoulder is as wide as the driving lane, and that's so that combines and farm equipment have space to run while traffic is progressing out there in the truck lane and the passing lane. So that longitudinal crack that you see there inside the edge line stripe, that's actually a longitudinal joint that is coming apart. And again, you got a very aggressive environment. So if you get a little bit of a crack there and water gets in it and freezes, it can push that apart, just like it does with the thermal crack. So that longitudinal crack, because of the length of it, and it went all the way through this project, we did mastic patching, and this is a little better picture. You can see how wide the shoulder is, but we did mastic patching of that longitudinal crack, which is a highly polymerized kettle mixed type of a sand size mix, and we did rubberized crack routing and filling there, as you can see in that transverse crack. So these are kind of types of cracks that don't fit the model of what I had previously described, and that's because of the climate and the practices up in Minnesota where that section was built. So here's another type of a transverse crack that doesn't quite look like that classic that classic thermal cracking that I showed you in that previous slide. And the reason for that is this is a joint reflection crack, and this is a project. I took this picture when I was crossing the road to go from a hotel to a restaurant to eat dinner. This is a project where they said, okay, we're overlaying jointed concrete pavement with asphalt, so we're going to go back and saw and seal on top of the jointed concrete joints to make sure we control the reflection of the cracking above that joint. But what they did was apparently, it looks to me like they used a roller wheel to record where the joints were instead of putting ground truth stakes or paint or anything like that to absolutely designate where they were. So when you went back and you used the roller and you identified the location where to do the saw cuts and the sealing, you were progressively off. So if you walk back to the beginning of the project, the cracking was exactly where the sawing and sealing was done. And the farther you got from the beginning of the project, the more off that was. And so that is not a thermal crack. That is not a fatigue crack. That's a jointed concrete reflection because of that misalignment. Another type of longitudinal cracking is edge cracking, and this is described in the LTPP manual. And this is a case where if you look at this, and you hopefully you can see the detail, but if you look at this, there's cracking along the edge of the paint, and then the pavement kind of sloughs off from that crack point. So sometimes you'll have you have differences in coefficient of thermal expansion. White thermoplastic reflects more energy than the darker asphalt. And so it's not uncommon to have cracking along the edge of the inside edge and the outside edge of the edge line striping. And then when you're in a geometry where you see the curve here and kind of going downhill, when trucks or really any vehicles, but in this area where I took this picture, there's a lot of timber activity. So when timber trucks kind of get over on that edge, they break that pavement off along that crack, and then it starts to wash out, and you can get a really significant drop off when that happens. So it's important for maintenance forces to stay on top of this and go back in and put some emulsion down and put some stone down to build that back up and to hold the edge of the pavement together, to prevent that from becoming a wash and becoming a safety hazard just due to vertical drop off. Well, all right. So when LTPP manual talks about surface deformation, that's rutting. This is actually a past research cycle at the track. I think this was a 2006 track, and it was part of an experiment where we intentionally collapsed the voids of mix to induce rutting, so that we could make a determination for the state DOT that funded the research. Where do you need to require removal and replacement with virgin aggregates and with neat asphalt as air voids collapsed? And so this is a neat picture because you can see the dual tire rutting. You know, we don't have a lot of this on the track, but this is one of the cases where we did, because it was an extreme rutting experiment, and rutting actually exceeded an inch. It was between 1 and 2 inches all along this test section. You can see us measuring the rut depth with a little portable straight edge there. And you can also use a wedge. If you don't have access to a really neat tool like that, you can just go out there with some type of a lightweight straight edge and a wedge with graduation marks on it, run out there, make a measurement real quick without taking any risks in traffic. It's not always rutting. Sometimes it's shoving and shearing of the mix. There's a picture of the kind of thing you can see typically where trucks are coming to a stop. That's when you can see that type of thing happen to mix. Patching and potholes also are described in the manual. Here's a picture of a really well done patch where it was saw cut out and then mix placed back in that saw cut area. Hopefully it was tacked really well. And then potholes can start for different reasons. And what you see in that picture actually looks like an area of local debonding and slipping. And then when that comes apart, it's a pothole that kind of originates within the pavement structure at the area where the slip occurred. Potholes can also occur because of soft bases and soft subgrades and water and all types of things like that. But this actually looks like some debonding is what caused that. And then that's some really ugly patching and some really advanced deterioration of pavement that can't be patched. If you have a very challenging pothole, this is a picture of a pothole that we repaired over on Lee Road 159 when the water line broke beneath the pavement, and that is a highly polymerized mastic patch. It's sort of a coarser mixed version of the patch that I showed you from Minnesota previously that we had used on that longitudinal crack. This is a deep crack repair, and we had tried several hot mix solutions that had failed over this water line break. And so Maxwell Products came in with their highly polymerized mastic, and just kind of as a demonstration for us, they patched that pothole. And I think we're 7 years now after that repair. There's not a single crack in that pothole patch. So that's outstanding performance. But again, from a forensics point of view, what's interesting about this picture is, first off, you see the great performance of this patch, but the water line damage, that's what you see down here in this area extending out from that patch. You've also got some some fatigue cracking and longitudinal cracking outside the patch area that's not related to the water line, but the cracking down kind of in the middle and the bottom of that picture is related to the water line. So for the purpose of data collection on Lee Road 159, we have to blank that data out so that it doesn't bias the experiment for that particular treatment. Now this is an example. This was actually on the 03 track where we had a slip, and the slip occurred, so it debonded between layers, and we think that it happened because where you see those dots, there are strain gauges on the bottom of the pavement. This was a 5-inch thick pavement, and the debonding was between the surface layer and the binder layer. It probably happened because there's a lot of foot traffic in that area where the instrumentation is. So we probably got some dust and kind of had a little bit of a negative impact on the tack between the layers. But what I want to show you is if you look at this from a forensic point of view and you say, okay, well, I need to probably patch this little area right here, then you're setting yourself up for failure, because if you step back and look at it, you can see that there's mixed dilation well outside of this lower area down here. So everywhere you see this dilation, that pavement is debonded. So if you really want to fix that and you want a permanent repair, a good practice is to go out there at night with your headlights and shine your headlights on it. And the shadows that are cast from the headlights, you can see many surface defects. You can see the whole debonded area, the whole dilated area. And then you can go in and saw cut it like we did here, get well outside the slip area. And in case of this patch, this was as good as you can possibly do a patch. We actually used the exact same mix that was in that surface layer, and we compacted it to the density of the original surface. And all of that was so that Dave Tim could continue his structural research without having the results confounded. And the outcome of that experiment was actually very positive. Very good repair. So also bleeding and flushing is a distress that's described in the manual. This is bleeding and flushing from some of the preservation treatments on US 280, the high traffic preservation treatments. This is a multi-layer chip seal. So you have multiple layers of emulsion shots with progressively smaller chips. I think this is actually a triple chip. So it's 7s under 89s under 10s. And so because of all the emulsion shot under heavy traffic, you have some migration of that binder, and you end up having some bleeding and some flushing in the wheel path. That's one of those treatments. The multi-layer chip seals can be an outstanding treatment, but it does better on the low volume roads than it does on the high volume roads because of the bleeding and the flushing. So I wanted to, before I hand off to Jason, I wanted to very briefly describe a slippage failure that occurred on Lee Road 159 within the preservation experiment, because it's a great kind of a forensics example. There's a hayfield off on the east side or the west side, actually, I guess, of Lee Road 159. And in this hayfield, there's a drainage ditch that runs and ties into the drainage ditch that runs down the shoulder of this road. So we had an extreme weather event, a lot of rainfall, the ditches flooded, and this was on Lee Road 159. We didn't do any crack repairs on any of the thin lay test sections. We just broomed and tacked and paved. So in this one particular test section, we had a slippage failure that occurred, and it was because water got up into the pavement structure through the cracks, got into the tack interface and caused this failure. And because this happened, it grew, it got bigger. We came in and did a repair with a BMD designed thin lay to have a little less mixed stiffness, and the replacement is still in service to this day and performing really well. So Jason, I'm going to stop my share here, and I'm going to hand off to you because I think that's your cue to jump in.
All right. Just want to confirm y'all are seeing the right screen.
I think we are.
Okay.
Looks good, Jason.
Can y'all see the pointer there?
Yes, sir.
All right. So yeah, Buzz mentioned the LTPP resource, the distress manual, and they also have a framework out. It was released in April of 2004, but it's still very relevant, and you can download it for free at the website listed above. Also, there's a NCHRP report 747, that was released a little over 10 years ago. But again, all of the information that is still relevant. A little bit of a long read. I think this one's around 160 pages or so, but a lot of relevant information there. If you're up late one night and just want to get something to put you to sleep. But I'm going to focus on the first few slides on some online resources. So when you're looking over these projects, the amount of information you have available may not be very extensive. In fact, it may be very limited. So it's good to tap into whatever you can online. And sometimes that can be as simple as pulling up Google Maps and loading up the Street View. So here we're seeing this was last taken in June of 2002. And on some of the well-traveled roads, those pictures are going to be much more frequent. On some of your county roads or your low volume roads, you may be 10 years between. So you may not have a lot of information there, but if you've got nothing but maybe just a window of when this project was originally paved or last touched, you can at least maybe help narrow it down. And then there's little things that you can get that non-pavement people might not even see. So those of us that actually look down at the road when we're driving down the road may pick up that there's some dark spots down here. So these are possibly oil spills or oil, something going on the road from these vehicles. And what could be causing that is an area of localized roughness where the vehicles are basically shaking when they hit that spot and shaking some of that oil loose. Or it could just be that that is starting to fail, and that is what's causing that roughness. So again, you never know where the piece of information is going to come from that's going to be useful. So always be open-minded to where you're getting it from. You can get topo maps online. Again, there's going to be several websites. A lot of these are free. You just got to have to search around and find the ones that have the area you're looking for. Weather or precipitation, historic weather data, that's usually available from federal sources, as well as the USDA puts out soil surveys, and certain regions of the country have, very uniform geography. Buzz has mentioned 159, and this is focusing on that area again, but you can see these sort of sublots where there's very different, at least buildups. So if you're working in an area or a region with, alluvial deposits or things that can vary, down even maybe on the half a mile scale. So this is probably about 1,000 feet, this stretch through here. So again, you can see how much it's changing, just enough that it's classified down into different zones. So be open to what is available online. Moving back into
Hey, Jason, can I jump in and make a comment on that previous?
Go ahead.
This is a resource that is really underutilized, I think, for forensic studies. And if you go to this USDA website, there's a ton of data that's like different layers that you can get to. You can even use this to determine, okay, I'm going to build a subdivision in this area, or I'm going to build a highway, or I'm going to build a campground, or I'm going to develop it in a certain way. It's awesome because it gives you kind of general starting point recommendations for all that based on the soil conditions and the work conditions and the location of the sites. I just wanted to jump in there and share with listeners. This is a great, like a forensic resource that doesn't cost anything.
Yeah, thanks. So moving back into some more of the technology-based, GPR, ground penetrating radar, has come on the scene in the last maybe 10 or 15 years in the pavement world. It's been around obviously longer than that, but it's something we're starting to see more and more. We run this periodically on the track. We usually have a vendor that comes in at least at the beginning or the end of each 3-year research cycle. And from the data I've seen, it's not all that precise at this point. So if you don't know a lot about the pavement, you may not be able to deduce exact layer depths. But where it's useful is you can quickly scan a road bed and you can see anomalies. So if there's like utilities like the water main that Buzz mentioned earlier, or just irregularity, something's going on funny underneath the surface that is not readily apparent, that will show up on the GPR. And here you can see how there's an abrupt layer change. And again, you may not be able to see if this is 2.5 inches, but you can start to see sort of just a macro scale and pick those irregularities out. And
Hey, Jason, can I jump in and make a comment there?
Yep.
The image that you're looking at is actually from the transition area between, I think it was between S4 and S5 on the test track. And so we needed to do some patching at that location, and GPR was really helpful to help us determine exactly how far the transitional depth went to know how far we should extend out the patching. So it was a very practical use of the GPR data that didn't require really sophisticated analysis.
And so these units keep advancing in both their precision and the speed at which they can be run. So instead of just having one sensor where you're having to do multiple passes down these lanes to get the full picture, you now have ones that are vehicle mounted that can scan the entire lane in one pass and do it at higher speed. So that technology is continuing to advance. One of our biggest tools we use here at the track is the deflection basins we get from the falling weight deflectometer, or the FWD. And on the track, we test this 3 Mondays out of the month because under the accelerated loadings, accelerated traffic damage that we do here at the track, it's necessary to get that full picture. Out on an open road, it may not necessarily be do it that much, but we're fortunate that we can shut the track down and we don't have to put up a lane closure to run these. But the data they provide is without being destructive, is invaluable. And the newer units, the fast FWDs, actually test much faster. They're around 5 times faster than these hydraulic units, the older ones that we're still using. The sensor package is still similar, but what you're generating is you're dropping this falling mass onto a sort of a padded or a rubber foot, and then there's an array of sensors that proceed away from that load zone. And so as you pick up that deflection basin, certain sensors will tell you what is happening on the surface, and as you proceed farther away from the load event, those sensors will tell you what is going on deeper down into the pavement. The FWD is a non-destructive test, but the more you know about the pavement, the more information you can get out of it. If all you know is that you have, maybe a 10-inch pavement, or you're not exactly sure where the interfaces are, you have to be there's a little more guesswork involved. But the more you can put into the modeling, the more you can get out of it. So for larger networks, one of the units that's come on in the last few years is the traffic speed deflectometer, or the TSD. So this uses similar technology as far as detecting how the pavement is moving, that deflection basin, but it doesn't do it by setting sensors on the ground. It uses lasers based here under the chassis of the trailer. And so it uses the weight of the vehicle to actually deflect the pavement under it. And these are continually getting more advanced, as well as incorporating other types of sensors. So these are LCMS, laser crack measurement system lasers that are mounted on the back. So they use surface imaging, and they have cameras and a laser system they'll give you a rut profile as well as also a distress survey. It is possible to add a second measuring beam if you wanted to measure in both wheel paths at the same time. Again, these vendors are trying to put as much on these units as they can, so it's more cost effective to just do one data collection as opposed to running multiple vehicles. So they can put GPR potentially, a texture laser will give you your roughness, as well as your IRI, as well as your macro texture. They're often mounted with high definition cameras to give you right of way. These are still very still new and very expensive. They're multi-million-dollar units, and you may only have 1 or 2 operating on a continent at a time. So it's not a tool you'll maybe see very often, but if you want a wealth of data for your network and you have the deep enough pockets to run it, they are valuable. Much simpler technique is dry drilling. So what we do with this, and when we've done it on the track, is you take a hammer drill and an auger bit, and you're not going to apply any water or any lubricant to cool that bit or to lubricate that hole as you're drilling, because we don't want to contaminate, we don't want to add any moisture. So we're going to bore through the asphalt layer and into the base or the subgrade generally to get a moisture content sample. Now you can use these to get a rough idea of how deep your different layers are. If there's enough of a color change that you can see between maybe your surface course or your binder course, your base course, it might be possible to deduce that. But you can see it's a small hole. So generally, if you're just going through the asphalt layers, you're not going to see that color change until you get down into the base or the subgrade. But once you are down into those lower layers, you're going to want to collect that sample. And so that's what we're doing here. We've got this sheet here that's collecting the sample, and you can see it's not a very large sample because it is a small diameter drill bit, but we want to save that out, sample it immediately, and get it locked away so that we can take those back to the lab. And so here's some of these cores. There are little dry auger holes that we've drilled. You can see they're very small. It's a fairly quick process. You can sample a bunch of different holes, and it's invasive. You are drilling a hole in the pavement, but I would call it minimally invasive. But maybe laparoscopic is the way to look at it. But you want to make sure as you still seal these holes back. So a high quality caulk or maybe a roofing cement. We're using a crack sealant. Off-the-shelf crack sealant to seal these back these days. But up in the top of the picture, you can see our moisture content tins waiting to be filled so we can take those back. And then last but not least, the tool we often use is the coring. I would say this is probably a pavement engineer's most useful tool. You can learn so much by pulling a core, but of course it is a destructive test. So looping back to what Buzz mentioned earlier on one of those test track sections, you can see from left to right how this progression of distresses proceeded through these cores. And so we took multiple cores over the section of pavement, trying to isolate and find that crack at different points of both initiation and propagation. So as he said, we had a weak bond between the binder and the base layers. And so you can see this tack coat layer right through here. And this is still an intact core, so it was pulled from a strong portion of the pavement. But then as this started to debond, we got an initiation of a middle up crack. So it debonded, and then this crack slowly going to work its way up to the top. And so in this fourth core, that middle up crack has proceeded all the way to the top, and you can see how it's marked here on the top. So this was actually visible before we pulled the crack, which is one way before we pulled that core, one reason we pulled this core in this particular location. Another thing I want to mention is, and I think Buzz mentioned it earlier, is the direction of traffic is often important for pushing these samples and understanding what you've got when you get back to the lab. It's real easy to go out there and pull a dozen samples and you get back and you realize you're not exactly sure of a couple of details that are important. But after that crack's propagated all the way to the surface, then it proceeded to go all the way through the base course. And so at this point, it's full depth, and we had rapid deterioration of this section. And so when you're pulling these cores, if the cracks are still very, very tight, this is still a hairline crack that we're investigating here. We went ahead and marked it on the surface and marked the crack location. And then there's a small arrow there that you can see that is marking our direction of traffic, because the shear plane, and if we're possibly going to do some bond strength testing, we want to make sure we're shearing those in the proper direction. But when you're pulling these cores, you're not just taking the sample. The core can tell you something as it's coming out of the ground or coming out of the pavement. So when you're pulling them apart, does it immediately fall apart? Is it barely holding together? Does it crumble in your hands? Does it get gummy? Do you have a binder gumming up on the teeth of the core bit? All those little things are important parts of the puzzle and can help you figure out what actually went wrong with this pavement. And so finally, like Buzz mentioned, we've both been down in the trenches, and like he said, this is literal. That was pun intended. So here we are marking the location of some trenches here just about a month ago from a failed section that's coming out on the track. And so we've got this longitudinal trench marked, and what you notice is this left side right here runs right down the middle of the left wheel path, and that's by design, because we want to catch on this cut face the inside, or the worst part of this transverse cracking here. Okay, and then in the background, we've got a full lane width transverse trench that ties into a longitudinal. So we've got a T-shaped trench there because that area was also of interest. But when we cut those with a wet saw, we pull all these slabs out, you can see all of these transverse cracks that are just popping out at you. And not all of them are visible from the surface. So like Buzz says, when you have those fatigue cracks, they'll start off at a certain interval, and that'll be fairly repetitive. And then as the fatigue crack spreads, it'll fill in the gaps between them, and that fatigue cracking gets tighter and tighter until you get that complete pothole formed. Just a personal tip that I'll mention is when you pull these slabs out, and I'd push them off to the side of the road and just put them on the shoulder, because obviously this pavement is coming out. You're going to have to mill it. So the milling machine will need something to ride over. So it's just real easy just to push those slabs back in where they came from. And sometimes they'll completely disintegrate on you, but it's much better than having to go and get a load of crushed rock or wrap to fill that hole so you can mill it out. And that's all I've got, and it's time for me to hand back off to Buzz.
All right. Can you see my screen, Jason, and hear me okay?
We can. Got it.
Yep, looks good, Buzz.
All right. All right. So we're gonna great job, Jason. Appreciate that. And we're gonna pull this thing together with some practical takeaways here. And the first one is, we talk about the NCAP pavement test track all the time as a proving ground for materials and mixes and structures and for preservation, but it's also I think Jason would agree, it's a great forensics training program, and we've learned a lot. It's been a blessing personally to be involved in it because you just learn so many practical lessons. And I would say practical forensics are important for both agencies and for industry. It's important for agencies when you're trying to use the most cost-effective way to come up with a good mitigation plan for a roadway based on what you're seeing. And being able to guess at pavement thickness, being able to guess at, what types of cracks are they, full depth, is it slipping, using these surface keys to figure all that out. It's important for agencies, but also for industry. If you want to bid a job and you're trying to figure out, hey, what are my patching quantities going to need to be? What are my repair quantities going to need to be? How thick is this pavement really? Not just the visual observations, but the dry augering methodology that Jason described. Very, very practical tool, and it's relatively non-destructive to do the dry augering as well. Third point, you can tell a lot about the structure just from surface appearance, just based on what you're seeing about the nature of the cracks, the orientation of the cracks, that type of information. Fatigue cracks can show up longitudinal if thick, but in the transverse direction if it's thin. So the way you see fatigue cracking is itself an indication of how much pavement thickness do you have. If they're showing up longitudinal, it might be 6 inches or more, and if it's showing up in the transverse direction, might be less than 6 inches. And then that can also be indicative of debinding. If you have debinding in between layers and you have the pavement responding like a thin pavement. Next point, you got a lot of practical tools available to you free on the internet. That TopoZone website, and then that USDA website. I have used that stuff a lot for some of the off-track analysis work that I have done in my career. As Jason pointed out, dry augering is useful for thickness. It's used for materials identification. It's useful for moisture determination, and then you can use a rubberized caulk to seal that hole back up, and then that way you'll prevent water from getting in there, and it won't have any kind of a negative impact on the pavement. Of course, all of this stuff, as we always say with our last bullet point, is always important in order for us to build and to maintain safe and sustainable asphalt pavements at the lowest possible life cycle cost. So that's it for our content. And as always, there's Travis's email address, and then mine and Jason's. If you have any questions specific about our content, you can take a picture of that or do a screen grab. Before I hand back off to Travis for for any kind of Q&A that we might have. I want to give him a plug for the Training in Your Pocket series that he has developed. These are awesome. I love this. I was in business for myself a few years between the DOT and NCAT, as I think Travis mentioned, and these little short training videos are amazing. 3, 4, 5 minutes long. They're engaging and entertaining, and they really do a great job of communicating basic principles. So hats off to Travis for that. And if you have not subscribed to that, please go ahead and do it. He also runs a very, very broad and deep training program for NCAT right now. He said he's up in Minnesota doing some airfield training. And so we can go do training for you, or you can come to NCAT to get whatever type of training that you need. So I would refer you to ncat.us, the NCAT website, if you want to learn more about the training program that Travis runs. And finally, I'm gonna hand back off to you for Q&A, Travis. But the next, by the list that I had, the next implementation webinar is June the 20th, and the same time slot, the third Thursday of the month, and the same time slot. And it's going to be kind of an overview of the significant things that we learned from the 2021 track. In other words, kind of a elevator overview of the track conference that we just held. So with that, Travis, I'm gonna pause my share, and I'm gonna hand back off to you.
Well, leave that up if you don't mind for a moment, please. I was going to mention on there that QR code right there is live. You can start registering for that webinar if you want to attend that next one that's coming up. Buzz, I think it's been great information here. We've got a couple of questions that have come in. I would love to get you guys to kind of answer those. The first one that we've got here is that with the middle up fatigue cracking on a low traffic or a low ESL road, you notice a difference in the crack pattern at the surface. So on that lower volume.
Wait, what was that? I'm sorry, Travis. What was that again?
So with the middle up fatigue cracking that we see from that debonding. So I love that set of slides that you guys have with the 6 sets, and you can see where the layers debond, and then the crack begins to propagate from the middle of the pavement section and come upward, and then propagates down again from there because we didn't get the proper tack coat in there. But with that type of a failure on a lower volume road, do you notice a difference in the crack pattern, or does it follow those same rules of thumb that you discussed?
No, I think on a low volume road, you see the same crack pattern. There are 2 sections on the track where we saw what you would think would be bottom up fatigue cracking from a relatively thin pavement, because it showed up in the transverse orientation, and both times it was because of something that happened in the middle of the pavement structure. So like one of the, from kind of practical forensics point of view, if you see debonding beneath the surface layer, you often see that show up as a slip, as that kind of that smiley face slip that then turns into a shallow pothole. But if you have debonding below the binder layer, a deeper debonding, then that shows up as a transverse crack, and that happens on low volume roads and high volume roads.
Jason, I noticed that you turned your mute off there. What's your input?
It's the same. Yeah, I didn't see any difference in crack pattern based on that middle up. But if he's done answering that question, we can move on to the ECR one. Okay.
Let's go ahead. So the next one is, what are your thoughts on the ECR modified asphalt, and do you think that it mutes the fatigue crack propagation?
I'll answer first, Jason, and then you can answer as well. I think there are some potential fracture benefits of engineered chrome rubber mixes, but I also think that's related to mix health. Like for example, if you take a dry stiff mix and you put something in it, I don't think you should expect to have good performance. But if you take a healthy balanced mix design mix that has both quantity and quality of effective binder content, I think that there's the potential for ECR to be a good investment, and that kind of is is a banner for the additive group experiment that we have on the track right now, and then some ongoing research that we have for the Oklahoma DOT with an engineered crumb rubber mix that's a balanced mix design as well. So the jury is out on how big of a benefit that it could be, but when you have an elastic black sand in your mix, which is essentially what the ECR stuff is, in my opinion, then you would expect there to be the potential to have some fracture benefits.
Yeah, and I'll just add, some of the best performing mixes we've had on the track have been rubber mixes. Unfortunately, we haven't been able to extend them to full failure, so we don't know where that bookend is. So yeah, the sealant is potentially high on those mixes.
And that's a great point, Jason, because there's two different types of rubber, in generally speaking, and the finer rubber you use in dense graded mixes, those are most of the mixes that people are running, and that's like the -30 mesh material. The coarser rubber particles, which is kind of a -16 mesh, that you use in the asphalt rubber gap graded mixes, and that's a great point, Jason. Those have been the most crack resistant mixes that we have evaluated, and so those have tremendous performance potential when you use them as surface mixes.
Yeah, great. So that debonding of the layers is such a big deal, and I know we hear over and over and over again about folks having trouble with their tack coat application. So this next question in here is asking if we could talk about the tack rate, and this was particularly in municipal overlays. Tom says here that he finds that the retacking is the best way to mitigate that middle up cracking, kind of on the cheap, I guess, if you will. But is there an upper limit to be cautious of? Jason and Buzz, I would like to hear what you guys have. When I was with the DOT, we did some investigating of this, trying to see where we were, and we did a half application of a full application of the rate we normally specified, a double and a triple, and then we pulled course and did bond strength testing, and we didn't find, even with the triple, that we lost strength out of that. Now, obviously, with the half, we didn't get the strength we wanted, but we didn't find that shear plane we sometimes worry about. I wonder if you guys have seen that actually happen.
Really, in my opinion, what we've seen, Travis, is that when milling is really good and there's no scabbing and it's a good good mill drum and good work, when it's cleaned up correctly, when you have a calibrated tack rate where the bar is set up perfectly and you get a perfect tack shot, then you got a lot of different tack products and a lot of different rates can give you outstanding bond strength. When in the real world, when you have you're out there in night paving and you gotta go and cover up and work fast, then what we find is that when you start to do kind of real world things sort of go wrong, you do need more tack, and essentially that's one of the takeaways from that section that had the middle up cracking. We did a forensic study in the laboratory, and where we had shot a kind of a textbook range of tack at a 0.06 rate with the emulsion that we were using. What we found was we needed a 0.1 rate. So that experiment really changed my philosophy on tack. And when we're doing studies, and we don't want the studies to be confounded by tack, by interface failures, I'm going to shoot a 0.1 with an emulsion unless there's a compelling reason not to do it. And if I'm shooting a hot liquid just with a dense graded mix, I'm going to shoot a 0.06. So I think a 0.06 residual rate is a really good place to be. Now, if you're doing an OGSC or an ultra thin bonded, obviously you're going to have way higher rates with that stuff. But and we get it that in the real world, when the humidity's high at night and you got to cover up what you milled and so forth, it's hard to do higher rates. But I think everything that we've seen is that good tack quality is super important to pavement performance.
Absolutely.
Okay, good deal. Well, we're coming up against the end of our time here. I do want to remind you, June 20th is our next webinar here. I'm excited to kind of give that elevator pitch, if you will, like Buzz mentioned, of the things that we did see in our track conference last week. With the training in your pockets, please, if you get a chance, just type training in your pocket into YouTube and you'll get there. And there is a crack type identification module in there that I think fits really well with this webinar here. That especially if you're trying to send somebody out that's not got the background of going out and looking at the different kind of distresses, it gives them an idea of what those different cracks mean. So given that, thank you all very much for your time. We look forward to seeing you next month.